All right. So we are back, and let's see if we can't now take some of these higher level concepts of like stitching together these nodes in memory and translate it to some actual code, but we'll do it step by step first before I actually start writing it in VS Code. So if Carter, you wouldn't mind helping me step through with some visuals, let me propose that line by line we solve some of the problems that we've just created for ourselves in building this thing in memory. So let's go ahead and first consider how we could build a linked list containing the numbers, indeed, 1, then 2, then 3. And let's translate each of those steps to code, and then we'll put it all together into something that actually runs. So how about the first step here will just be this, to declare a pointer called list that initially has no value, at least at this point in the story. List is the name of the variable. Node star just means that this is essentially going to be our little square over here that points to the beginning of the list. Of course, it's ideal if it ultimately has a value, because when we initially call this line of code, it just gives us, indeed, that square over here on the left, but it's got a garbage value because there's no equal sign on the other side there. So let's propose that we do one more step here and actually initialize it to null, so that if only we know that it's not garbage, it at least has some known value. And null is a good way of signifying that at this point in the story, the list is empty. Indeed, null indicates there's no nodes in the list. So that picture would now look like this, whereby let's just draw, instead of writing null everywhere, I'll just leave the squares blank when it's not a garbage value per se. It's literally OX0 or null. All right, so that's it for building a linked list of size 0. Like, we're sort of done then, but we want to now add a 1, and then a 2, then a 3. So next step here might be this. If I want to allocate the first of my rectangles on our previous picture, I'm going to call malloc, and I'm going to ask for enough memory to fit a whole node. Now, technically, I think that's going to be like 4 bytes for the int and 8 bytes for the pointer, even though I did not draw it to scale on the board. So that's technically going to be, what, 12 bytes? But again, size of node just figures out how many bytes I actually need dynamically. That's going to return to me the address of that chunk of memory, which apparently I'm going to store inside of a temporary variable called n for short, for node. But let's see what this does pictorially. So when this line of code is executed, I first get on the left that variable n. It's got a garbage value by default because I haven't executed the whole thing from right to left. Meanwhile, on the right-hand side of the expression, I've got now a node somewhere in memory. It happened to be free here. This is where malloc put it for me. But it does have 2 garbage values initially. But because it's a node, per my type def earlier, every node I proposed is going to have a number and a next pointer. So we can see those labeled here. But they've got 2 garbage values initially. But all I care about initially is that ultimately n is pointing at that chunk of code. So initially, if we could back up 2 steps, we have 2 steps. So we have one step forward. We have this line of code gives us this variable here, which has garbage. When this side of the expression is executed, that allocates the memory. And then when we copy from right to left the address of that chunk of memory, that's what gives us conceptually this arrow, and the garbage goes away because that's a valid pointer now. Of course, there's still 2 garbage values there because we haven't set this node to store a number like the number 1. So let's go ahead and execute one other line of code like this. Oh, do I want to do that? Let me tiptoe over here and change this to change the story temporarily. Sorry. We'll cut this out of the video. They were out of order. Slight spoiler. OK. OK, so now pretend that didn't happen. OK. So now, of course, we have to put the number 1 into this first rectangle. So let's do a line of code like this, which, while cryptic looking, is just an application of ideas we've seen in week 4 and prior. Star n means to start at this variable and go there. Follow the arrow is what the star or the dereference operator does for us. And then the dot operator, recall, when we first introduced structs, like for a person struct, allows us to go at the number field or the next field. So if I do star n, and then in parentheses to make sure order of operations is preserved, dot number, that allows me to set the top of those boxes to, I should have fixed this earlier. That allows me to set the top of these boxes to 1. Sorry. Fix this. Do I want to do that? OK, sorry. Do this. OK. We won't restart the whole thing, though. OK. So this line of code means go there, access the number field, and then assign it the actual number 1, which puts the 1 in the top of that rectangle. Now, admittedly, this syntax is not very user-friendly. It's annoying to remember. You have to have the parentheses. So there's another syntax for this. Whenever you're doing two things like this in code, dereferencing a pointer that is going to an address, and then further using the dot notation to go inside of the structure you find that, wonderfully C gives us this syntax whereby you can just change the star and the parentheses and the dot to just be an arrow. And again, it's not a single character on your keyboard. It's a hyphen and then an open angled bracket. But I kind of like the semantics of this because this code now pretty much matches the picture. N arrow leads you to the value that you want to access or ultimately change in this way. So now, at this point in the story, we have a linked list of size 1 that only stores the number 1. Suppose now we want to add the number 2 to the list. Well, let's see how we might do that. And we'll do this a bit more quickly this time because the code is similar in spirit. So if I now do, damn it. I'm sorry to keep messing up the story. There's one step, though, we've forgotten, of course, which is that we can't leave this garbage value here because the garbage value is some unknown value that effectively is pointing who knows where. And we don't want to accidentally misinterpret that garbage value as being a valid address and risk going there. So, of course, what value should we put here instead? Our old friend null, just to signify that this is indeed the end of the list. And we could do that with a line of code like this. And again, we'll connote as much by just leaving that empty box blank. So now we have a list of size 1. Let's go ahead and add the second number to it, as with these lines here. List equals n allows us to remember that indeed we have this list here. So if we can step one step forward, here's what the picture now looks like. And technically, let's go one step further here. This is now really what's going on in memory once my list of size 1 exists. My main variable called list is pointing at exactly that first node. At this point in the story, I don't need to know or care about the temporary variable that I called n, even though it might very well still be there. But indeed, this now represents that linked list. Let's now indeed add the number 2. So with the same line of code as before, I'm going to allocate another node, size of node. Ideally, I would be checking for null here, but we're doing the juicy parts only on the slides. Let's now go ahead and depict that. So what happens with this? This brings back our n pointer, which might have been there the whole time, but we're doing this step by step. It's a garbage value, though, because we haven't yet copied from right to left. malloc, of course, gives us a second chunk of memory, which maybe ends up there with 2 garbage values by default. I've omitted the labels now just because they're still going to be number and next, respectively. Once we copy from right to left, that changes the garbage value to actually point to that node as before. Now, if we want to populate this node with the number 2, we do a line of code like before, which allows us to start at n and then follow the arrow, updating this here to be 2. I'm sorry. I should have caught these earlier. My bad. Not Carter's fault. This should be gone. This should be gone. Apologies. User error. Let's not mislead. Wow. OK. That's a lot of regrets. OK. Adorable, though. OK. OK. Wow. Wow. Oh, if only I had a 10-minute break that I could have fixed this. Slight spoilers, clearly. Sorry. OK. OK. So we see where this is going. Sorry, Carter, to put you on the spot here, too. OK. So sorry for video. All right, so here's where we left off, where as soon as we actually go one line back just so we can see the code. OK, one line forward. Wait, one line back? Yes, OK, sorry. Now I'm just being stupid. One line back. One line back. This way. OK. OK, sorry. OK. After this week, it's smooth sailing. So here we have now, on the right-hand side, the return value of malloc gives us the address of memory we've allocated. The left-hand side is this pointer. And as soon as we do the assignment from right to left, the garbage value effect. Wait, I thought we fixed this. Wait, he's still there? Oh, my God. OK. All right. All right. So here we go. OK, so I'm very sorry. Where we pick up is here. malloc is going to return the address of the memory that we want to store this new node in. N is going to be our temporary variable down here, whose value is initially a garbage value because it's not yet been assigned. But now when we finally assign right to left, the garbage value indeed becomes an arrow. Oscar disappears because it's now indeed a valid pointer pointing here. Now the values themselves, number and next, are invalid, garbage values. So here is where we can now start using our new syntax, like the arrow notation, or the star and the dot if you prefer. And we can change the value of n, follow the arrow, to number, and that becomes 2. Similarly, we can do this again and set n arrow next. So start at n, follow the arrow, access the next field, and set that equal to null. Now, we're not quite done yet because we haven't actually linked things together. So here's now where things get interesting. How do I combine these two? Well, let me propose this. Let me propose on our next line here, we actually update for now list equal to n. That is to say, whatever address this is, whatever it's pointing at, change list to be the same address. That is, point at the same thing. So if n is pointing here, let's change list to point here. And go ahead and do that, Carter, if you could. I don't like this. Can you go one further step? This is bad. I got ahead of myself here, this time intentionally. What is wrong about my sequence of operations here, where I updated list to point at my new node? Yeah. Yeah, we lost the pointer to the other node. So I don't even care about the ordering, 2, 1 or 1, 2. The bigger problem now, as the lack of arrows over there suggests, is that I have a memory leak. I have orphaned my original node in the sense that nothing is pointing at it anymore. Now, absolutely, I could fix this by adding some temporary variables. I could add it to the mix. But at this point in the story, I have not done any such recollection thereof. So let me back this up, and let's go forward in the slides. This is where we left off a moment ago. I think I need to take into account order of operations. And I'm going to keep this simple. I'm not going to care about the order of the numbers for now. I'm fine with a list that is 2 and then 1. So with that said, let me go ahead and update, I think, this box here to point at my original node. So let's see how we can do this in code. OK, n arrow next. So n arrow next should equal the current list. And this is a little weird again, but recall what list is. List is this pointer here that just contains the address of the original address of the list. Or, equivalently, it contains this arrow, whatever it's pointing at. So what this means in this line of code, n bracket next means start at n, follow the arrow, access the next pointer, and set it equal to whatever list equals. So if list is pointing here, then next should point there as well. This, I think, is safe because now we have redundancy. Now we've got 2 pointers pointing at the original list. And now I think we can do another step whereby we update list to equal n. Same line of code before that got us into trouble, but I'm doing it second now instead of first. When I execute list equals n, this now sets list equal to the same thing that n equals. And so now I have successfully inserted my new node containing 2 into the list. And in fact, if we advance one more, we can just clear up the clutter, assume that the temporary variable is gone from the story. Now we have a linked list where, admittedly, ordering is wrong. It's 2, 1 instead of 1, 2. But at least it's linked correctly. And I didn't orphan or leak any memory. Questions on this sequence of steps here? Yeah, in back. Yeah, spot on. So this would fall under that category of a stack, if you will, although I've not called it that by name because I just pushed the number 2 onto this data structure, if you will. And indeed, it ended up at the beginning of the list instead of the end. And so here's where we see a distinction between an abstract data structure, which is where we began. A stack is a thing like the pile of sweaters that just has push and pop properties and LIFO access, last in, first out. How do you implement something like that in memory? Well, it would seem that you could implement the notion of a stack here, not for sweaters, but for numbers, using a linked list, so long as you implement insertion, aka pushing, by prepending new values to the list, by prepending again and again. And if, Carter, you don't mind hitting the keyboard one more time, if I wanted to add the number 3 now, you could imagine prepending it to the list. Why? Well, honestly, especially as this list gets longer and longer, I kind of like the appeal of prepending these elements. Why? Because even if this list gets crazy long and way, way out here, you didn't notice me following all of the arrows earlier to do the insertions. If I want to insert a fourth number, a fifth number, a sixth number, all I have to do is like insert it here, if you will, point it at the original start of the list, then update this pointer, and done. And I would say that's like 2 steps, give or take. It's not going to be n steps, as it would be if I had to append the new nodes to the end of the list. Now, of course, we've sacrificed ordering of these numbers. They're literally in the opposite order, or whatever order they were inserted in. But that might very well be OK, depending on the goal at hand. All right, thank you to Carter for stepping through this. What if now we wanted to translate this? Oh, sure, thank you. It's all for you, none for me in this example. So here we have perhaps a way of translating this now to some actual code. And this will be the last of like the sort of intense code here, just to give you a sense of how we can translate this idea now to actual steps. So this is List.c in VS Code here. Let me go ahead and make a couple of changes up top. Let me go ahead and how about declaring a node using typedef, struct node using our new framing as before. I'm going to give every node a number, as I proposed, and every node a pointer to the next element, which is going to be implemented just as before. And I'm going to simplify the whole name as just node. So all of that is the exact same typedef that we proposed earlier. Now, let me go ahead and get rid of all of this code, which we wrote earlier, and recall that this was the most recent version that was not a linked list. This was just an array that we allocated and then reallocated. So this is sort of the old way of doing things, but it was inefficient because we might have to lean on a for loop or lean on realloc to copy everything around. We're now going to re-implement the notion of a list as an actual linked list, not as an array. So my main function now might do something like this. And I'm going to really just copy the lines of code that we just stepped through on the board. So let me give myself a special variable called list that's going to be initialized to null. And this is just my pointer, the square on the left-hand side of the screen, that represents the start of the list. And if it's null, it means the list is empty. So done. I'm done implementing a linked list of size 0. Well, now, how do I want to run this code? Well, let me propose, for the sake of discussion, that this version of the program will take command line arguments. So I want to be able to do something like this. I want to run this program ultimately and type in 3 command line arguments like this, 1, 2, 3. And I want my program in a couple minutes to allocate 1, 2, 3 nodes and stitch them together, just like the visualization on the board. I could use getInt, but it's just going to be faster if we use command line arguments. So again, I'm just borrowing some concepts from week 2. But none of that's possible yet until I change my code here. So let's do this. Int argc, string argv. But you know what? We know that strings are not actually a thing anymore. So I can change my command line argument definition to be what it really is. It's really char star. But it's the exact same thing as in week 2. Just strings are no more, at least without the training wheels on anymore like last week. And now let me do this. For int I equals 1, I is less than argc, I++. So what I'm doing with this loop is I just want to iterate over the command line argument. So I have one number at a time from the prompt. What else do I want to do here? Well, let's go ahead and how about do this? Let's get a number. So int number equals argv bracket I. So a couple of notes here. 1, I'm starting my for loop at 1 instead of 0. But I'm going up to argc. Argc is argument count, how many words are at the prompt. Why am I starting at 1 instead of 0, though, given my goal? Why am I starting at 1? Yeah. Yeah, so the first value in argv is actually the name of the program. That's obviously not a number, so I want the second value. So I'm going to start iterating over those command line arguments at I equals 1. So that's all. I just want to get the actual numbers at the prompt. Unfortunately, argv bracket I is a string, aka char star. That is not an int. So this line of code won't work. But can anyone think back to like week 2 where we had a function for converting strings to integers? Anyone? Yeah, so a to I is a function that converts ASCII to an integer, assuming what you give it as an argument looks like a number, like 1 or 2 or 3. So let me fix this. Let me actually do the conversion. If I were really being careful, I would error check this, make sure that there's no digits, just like you might have in problem set 2. But for today's purposes, I'm just going to assume the honor system that the user, me, is going to run the program correctly. All right, so now that I have a variable containing the number from the command line, let's just allocate a node for it. So let me do node star n, just like we did in the visualization. And let's malloc enough space for the size of one such node here. I now need to just be super safe. So if n equals null, like if I'm out of memory, you know what? Let me go ahead and just immediately return 1 here. Otherwise, if that's not the case, let me go ahead and update the number field of this new node, which at line 24 does exist because it did not return null. So I did not exit early with return. And let me just store whatever number the human typed in first. So the return value of a to I, which per line 17 is in my variable called number. And then let me go ahead and just prepend this to the list. Let me go ahead and say that this next field first has a known value null, just so that we get rid of that second garbage value. And let me go ahead and now prepend it to the list. So if I want to prepend it, that means this new node must have a next field that points to the current beginning of the list. And again, the goal here is to prepend. So whatever the current list is, let's change it so that this new node points to that existing list. And now, step 2, as before, was to update the actual list to point at this node. So recall in red on the screen before, I screwed up originally, and I only did this line by moving the pointer too early, if you will. But I fixed that once Carter helped me rewind, and we got rid of the red line, which indicated error. And I just do n arrow next to change the next field of this new node to point to the existing list. So I'm not orphaning anything. All right, at this point in the story, I think my code is correct. Not batting very well, though, today. But I think my code is correct. But the program doesn't do anything interesting. So it would be nice to kind of now iterate over this linked list in memory, whatever its order is, and print things out. Well, how do we do that? Well, it turns out if you want to iterate over a linked list, the general paradigm is to do something like this. To define a temporary variable, I could call it temp, but another convention that you might as well see is called pointer, PTR, for short. But you can call it anything you want. And you can have a temporary variable first point at the first node in the list. And then in some kind of loop, like a while loop, you point it at the second node in the list. And then you keep iterating. You point it at the last node in the list. And then eventually you iterate too far, effectively pointing at null, at which point your while loop can presumably terminate. So how do I implement that idea of allocating a temporary pointer that just points at each node in the list and lets me print out, ultimately, each of those numbers? Well, let's go back to my code here. And let me do this. Let me go ahead and declare this temporary pointer, which is going to be a node star also. Why? Because it's the address of a node, the first, the second, the third. And I'm going to set that equal to whatever the beginning of the list is. So that is going to be equivalent to this version of the picture here, where pointer is just temporarily pointing at the first node in the list. It's not pointing at list per se. It's pointing at the first node in the list, which list is also pointing at itself. All right, once I've done this, I think I can translate this to code that's a little new, but it's conceptually familiar perhaps now, while that pointer does not equal null. So while I have a valid pointer, like my finger or that arrow is pointing at an actual node in memory, well, let me go ahead and print it out. So let me print out with %i\n whatever is in the current node at the number field within. And again, this is going to have the effect, hopefully, of first printing the 3. And I think I just need to now update the pointer so that on the next iteration, it's pointing at the next value. So if this is where the story is, how do I update pointer to point at the second element of the list? Well, I want pointer to point at the 2, and I want pointer to eventually point at the 3. Well, how do I do that? Well, the way in code I can follow these arrows is as follows. If I currently have pointer pointing at this node, but I want to point it at the next node, I can borrow this pointer here. So whatever this address is in the first node, aka the next field, I can copy that into pointer. Because then pointer will point at whatever this is pointing at by just setting one equal to the other. So once I've done that, the picture will become this. And how do I translate that to code? While new syntax is surprisingly straightforward, all I need to do is say pointer after printing it equals whatever pointer currently is, but grab its next field instead. And this is a very common paradigm. When iterating over a linked list and you're using some temporary variable like pointer, you can simply set pointer equal to pointer next. And what that means here is as follows. If this is pointer, pointing from here down to here, pointer next is follow the arrow, grab the next field. So if you set pointer equal to this thing, that's the same thing as pointing this at this same box. And indeed, if I advance to the next slide, even though the arrows are technically pointing at different parts of the rectangles, that's just for graphics sake, pointer is now pointing at the second node. And when I do this again on my next iteration, it points at this. And then this last step, notice, when I keep doing pointer equals pointer next, this will become eventually this value. But what's this value in this linked list? It's null, technically. So this arrow will eventually take on this value when I set pointer equal to pointer next. And at that point, PTR, my temporary pointer, is going to be null. So it might as well look like this pictorially. And what does that mean for my loop? Once pointer is null, because you've walked off the end of the linked list, what's going to be true of this loop here, started in line 32? Any observations here? What's going to be true? What will happen now as soon as we hit the end of the list? Yeah, sorry. The loop is going to break out. Why? Because line 32, which is constantly asking, while pointer does not equal null, well, if pointer finally equals null 3 steps later, the while loop is now done. And so what I can do at the end of this program, once I've printed out those values, well, first let's go ahead and open my terminal window. Let's make list. OK, compile /list. And let me try the same values, 1 and 2 and 3. That's going to, again, allocate 1 node, 2 node, 3 nodes by prepending each of those values. And it's then going to iterate over them from left to right. And so when I hit enter now, what should I see on the screen if my code is correct? What will I see? Feel free to just call it out. 3, 2, 1, because I've prepended presumably. And here we go. I indeed see 3, 2, 1. So the list is backwards, but all of the elements are there. Now, technically, if I ran Valgrind on this, Valgrind would not be happy because I have never freed any of my memory. So I should probably now have a second loop here that does something like this. Let me again set pointer equal to list. I don't need to redeclare it because I've already created this thing on line 31. I just want to reset it to be the beginning of the list again. And now I can do the same kind of thing. While PTR not equals null, go ahead and do this. Well, I don't want to just do free pointer and then do pointer gets pointer next. Why? My goal is to free all of my memory, but I think this is going to get me in trouble. Pointer equals list just gives me a temporary pointer that points at the 3, and then eventually the 2, and then the 1. How? Well, while pointer not equal null, I'm freeing the pointer. So this is like saying to malloc, free that node, free that node, free that node. But what's the problem with what I've just done here? This code is technically buggy. Yeah. Exactly. After you call free on pointer, you are, by social contract with C, not allowed to touch pointer anymore. It is invalid. Now, it's still going to be a number. It's still going to be a pattern of bits, but it's invalid. And you'll very often get a segmentation fault if you tempt fate in that way. So I can't free the pointer and then use it literally the next line. The solution here, kind of like our swapping of the liquids last time, was to maybe just have a temporary variable. So I can do a switcheroo. And so a common way to solve this problem to get the order of operations right would be to do something like this. Give yourself a temporary pointer like node star next. Set it equal to the place you want to go next. So one step ahead. Now you can free pointer. And then you can update pointer to be that next value. So essentially, you need like 2 hands now. You create on line 41 another pointer that if this is pointing at the first node, the 3, your new pointer is pointing at the 2 temporarily. So now you can tell malloc via free, release this memory, but I haven't forgotten where I want to go next. And so I can now continue on. So a common paradigm for just iterating over these nodes and then freeing them. A couple of observations. Strictly speaking, I could have consolidated this. I don't need 2 loops to print the nodes and then free the nodes. I could do that all at once, but let's assume that there's other stuff of interest in my program, and I don't want to just immediately free it. There's one other bug that I should probably address here. There is still a potential memory leak up here, and this one is super subtle, though Valgrind would help you find it. Notice that in this loop here, when I'm calling malloc, this line of code is fine if the first line of malloc fails and returns null, because I immediately return and I'm done. But what if the second call, but not the first, or the third call, but not the first or second fail? This line of code has me returning immediately. You really need to do some garbage collection, so to speak, whereby you really need to go in and free any nodes that you did allocate successfully earlier. Honestly, that's going to be a pain in the neck. We won't do that here. But probably what I'd want to do is write a function called freeList or something like that, and call that function to free any nodes I had previously created. So it's not quite at the finish line, but the building blocks are indeed here. Questions on this code? And I think it's safe for me to promise that it won't escalate further from that. Questions on this? No? Well, let me show you one alternative that you might prefer. And I'm pretty sure this isn't an escalation. It's just an alternative formulation. Another way you can iterate over nodes in a list could be this. Instead of a while loop, for instance, let me actually show you one other piece of syntax here. You could technically use a for loop. You could give yourself a node pointer here that is initialized to the list. You can then check in your for loop that it's not equal to null. And then you can do your update as usual like this. Either of these are equivalent, even though this one I suspect looks scarier. It's doing the exact same thing in one line instead of 2. But there's no reason we can't use for loops instead of while loops to achieve the same idea. But I'll leave these two as demonstrations of one approach or the other. But that's just like in week 1, for loops, while loops, whatever looks simpler to you. Even though admittedly neither of these probably looks super clean. All right, so let's take things back to things more conceptual here. Up until now, we've been inserting elements into this linked list by prepending them. Let's consider what the running time then is of these operations. So if I've got a linked list of size 3 or size n more generally, time has passed and I've added a lot of things to it, what's going to be the running time, for instance, of searching a linked list for some value? And I'll tell you already, it's not log n, because again, binary search is off the table, as per before break. So what might the running time be of searching a linked list for some value, like 2 or 3 or 1 or 50? What might the running time be? Oh, O of, I heard it over here, O of n, and why? Who was that? Oh, in the middle here? Why O of n? Exactly. You're going to have to go through every item in the list, starting from the left, from the beginning, which is how we've been drawing things and connecting the dots. And in the worst case, the element might very well be at the very end, so it's going to be big O of n. What about insertion? How many steps in terms of big O notation has it been taking me to insert elements into the linked list using this prepend design? Yeah, so it's technically constant time, big O of 1. And again, 1 is just representative of any constant. It could technically be 2 steps or 3 steps or even 10 steps or 100 steps. But if it's always finite and fixed, then indeed you can say it's in big O of 1. Now, why is that? Well, again, no matter how long this list gets, so long as there's memory available for me, I can just kind of create a little splice at the beginning of the list to put in the new node, update the original list, and I'm on my way. And it keeps getting longer, even though it might not be spread out in memory. So big O of 1 is possible with these linked lists if I indeed prepend things. Of course, if I prepend things, everything's going to get out of order, potentially. And we're going to have maybe the stack property instead of a queue property. So we might want to do things slightly differently. So instead of doing this, whereby we kept prepending, suppose we append to the end of the list instead. So if we now insert the 1, the 2, and the 3, as we might want to for a queue to maintain that fairness property, we might start with an empty list. We might add the 1. We might append the 2, append the 3. And so it just is sort of laid out differently in memory. And again, if I can come to you in the middle, what's the running time of search? Again, when the linked list uses this append implementation. Yeah, still big O of n, because in the worst case, you're going to have to go through the whole list just to find it. And notice, it doesn't matter if you have an intuition now that the bigger numbers might very well be at the end. You have no way to jump to the end. You have no way to jump to the middle or do anything resembling binary search. Every search has to start from the left and follow the arrows again and again. All right, so I don't think we've done any better there. And in fact, what is insertion's running time now in big O, when we're appending to the list in this way, as we might to implement a queue instead of a stack? What's the running time of inserting a new value? Big O of? So not big O of 1 in this case, but big O of n, because if I'm appending, by definition, I have to start here and traverse the whole thing looking for the end. Now, this is a bit of an overstatement, right? You could obviously optimize this slightly by maybe adding another variable that always points to the last element, sort of a cheat sheet, a shortcut that gets you all the way to the end. That's totally fine. It doesn't really fit the traditional definition of a singly linked list, but there's absolutely smart engineering solutions to these kinds of problems. But as designed, it would indeed be big O of n to insert to if you've got to go all the way to the end and you're not using a little extra memory to get yourself there quickly. Well, what if we want to take things one last step and not just append blindly? Because even though I inserted 1, 2, 3, if I inserted them in random order, they would end up in random order. What if you want to maintain a sorted list from smallest to largest? Well, then you might want to insert numbers like this. Starting from an empty list, we might have a 2. Then we might try inserting a 1, but we want to keep it sorted. So now we're going to prepend in our code. But then you might want to insert a 4. So you would append the 4, because you're probably going to look for the right spot to insert it. Then we're going to insert a 3. And this one's getting a little annoying, because now you have to like iterate over the list, look for the right spot, and then do a little smarter of a splice. But it's possible. But you don't want to orphan the 4, for instance. And then ultimately, we get back to this question. What would the performance be of your linked list if you're trying to maintain sorted order? Well, search, I think, is going to be big O of n for the same reasons as before. What about insertion? Big O of what? For inserting into a sorted linked list. Yeah, in the worst case? Yeah, it's still big O of n. So it's no worse than, but it's not really any better than appending. But we gain the additional property of maintaining a sorted list, which might very well be useful if you're sorting your contacts in your phone or something like that, where it just makes sense to maintain sorted order. Now, in the code for online today, if you take a look at some of the final versions of code, like list6.c and list5.c, as we'll post on the website, you can actually see code that will solve all 3 of these problems. The prepend version that we wrote live, the append version, which we talked through, as well as this sorted order one. But I think I'll avoid showing it live just because I do think that starts to escalate quickly. But I think we have enough of a building block, if we're comfortable with prepending, to at least solve some real world problems with these linked lists. Questions then on linked lists, which we'll now leave behind on their own, but now use this technique to solve fancier problems, but much less code. Questions on linked lists?